Good morning, everyone, and good afternoon, depending on where you're joining us from, to this webinar on seismic forward modeling. My name is Eric Torrio. I'm the Director of Business Development at Acceleware, focused on the seismic imaging part of the business. And joining me today is Greg Cameron, Processing Manager at Thrust Belt Imaging, who will be doing this presentation. So thanks for joining us. Let me bring up the agenda. This is a brief agenda of what we'll be going through. I'll start off with some introductions. Greg will introduce Thrust Belt Imaging and do his presentations, and then we'll have some conclusions and time for questions and answers at the end. Now, during the course of the webinar, which should last about 30 minutes long, you'll have a chance to type in your questions in your webinar chat window. So feel free to type in the questions. We'll collate those and we'll answer them at the end. If we don't have time to answer all the questions, we'll make sure we'll follow up with you at a later time, and hopefully not too soon after the webinar. We'll save this webinar. We'll put it up on our website. You can look at it at your leisure afterwards as well. So let me briefly introduce you to what we do at Acceleware, what Acceleware is all about. Some of you may not have heard much about Acceleware. We're a high-performance computing software developer, and we've focused on the development of seismic imaging technology, and we also, so namely the products that we're talking about today for seismic forward modeling, but also reverse time migration and full waveform inversion. But we also do a lot of customization and software developments for various companies, taking development code and turning into production-ready software. We're Calgary-based, but we've got a global presence, and we work with companies around the world, from super majors, national oil companies, small companies, consultants, so the whole gamut. So today we're going to be focusing on a seismic forward modeling, a product that we call AxWAVE. It's a finite difference forward modeling application. It's been primarily used in the design of seismic acquisition, but also for geophysicists, interpretive geophysicists who want to run what-if scenarios. They want to run, for example, a wedge model, what that might look like to run a wedge model. How do they compare to the real seismic data through their interpretation? Seismic interpreters can use this tool as a validation process to their interpretation. And but what we're going to do today is focus on how you would use seismic forward modeling in a seismic processing environment when you need to better understand the complexities of imaging in complex geology areas. So to that, I will pass it on to Greg, who will introduce Thrust Belt Imaging and run this presentation for you, and I'll join at the end.
All right, thank you, Eric, for the introduction, and thank you everyone for coming to this webinar. Today, I want to share several examples of how Thrust Belt Imaging has used AxWAVE forward modeling to help us better understand our seismic imaging challenges. I'll start by giving you an overview of TBI and what we see as our imaging challenges, and describe our pre-stack depth migration workflow. I'll then show you several modeling examples that address issues such as anisotropy, how we sample our travel times in our pre-stack depth migration, and how we incorporate a more detailed near-surface model into our velocity model. Talk about some of the further work I want to do using AxWAVE, and then, like Eric said, we'll have time for questions. And please type your questions in as we go, and we'll collate them and look at them at the end of the presentation. So Thrust Belt Imaging is a seismic data processing company. We're focused on complex structured land data. We were founded in 2004, and we're Calgary-based, but have worldwide experience. You can see on the map on the top left a selection of our 2D and 3D projects. So we do have extensive experience in compressional and extensional basins around the world. And in the bottom right, I'm showing a picture of Canada and Colombia, saying, we developed our experience in Canada, but it's equally applicable to geologic settings around the world. So what challenges do we see in complex structured land data? Well, there's almost always a complex near surface. So we have complex weathering, fracturing, steep dips, anisotropy. And we usually have fairly poor signal to noise in our data due to near surface scattering, due to the complex near surface. Often poor source and receiver coupling, depending on the real near surface and how we can access for our shots and receivers. And we'll see some illumination issues depending on the geometry and the velocity complexity of the subsurface. Often we also see sparse source and receiver sampling for a variety of reasons. It is expensive to work in these environments, and so cost is an issue. And also we have access issues. It's difficult sometimes to put geophones up a cliff or through a river, and there's also sort of lockout zones that we have to deal with. So here I'm showing an example of a pretty good quality result we got from the Benjamin Creek 2D line in Western Canada, the final PSDM model on the left and image on the right. And this is on the good end of the type of data we see. Often we don't have this much reflectivity or this complex a model. And in general, what we find is that automated tomography methods tend to not work so well on these types of data. Because of that, at TBI we take an interpretive approach to our velocity model building. So it's guided by client interpretation, well information, surface geology. And we use our seismic diagnostics, including event continuity, fault sharpness, and gather flatness, and also well ties to drive our model updates. I've got a schematic on the left here showing what our velocity model building routine looks like. So we'll start with our interpretation and use that to build our velocity model, use our velocity model to migrate our process gathers, and then evaluate whether we've optimized the image and how well our wells tie. Most likely not very well for the first few iterations, so we revise our interpretation, update our velocity model, and repeat this loop. And we may go through 5, 10, 30 plus iterations depending on the complexity of the data and the complexity of the model. Once we're happy with the result, we apply some post-processing and output final segue volume. So why are we wanting to run modeling studies using AxWAVE? Well, really it's to better understand our imaging challenges in the tough geologic settings. With our poor signal to noise data, we often don't see a lot of these challenges in a very straightforward way on our data, so we'd like to model them to understand them better. And specifically, we're trying to understand how we can improve our image with a more detailed near-surface model. The near surface is the lens through which we see the subsurface, so any resolution we can add to the near surface should help us with our imaging of deeper reflectors. So I'm going to show 3 different case studies here to show you how we've used AxWAVE recently. The first one is going to deal with anisotropy and how does near surface anisotropy impact our image. Then we'll look at how we need to resample our Kirchhoff ray tracing for higher resolution models, and then I'll talk a bit about how to build an appropriate near surface model and what we can compensate for with statics. So this first example, this is a production project we were working on where we noticed that a key reflector suddenly degraded laterally, and we had some surface geology information that suggested we had steep dips at surface and it was a highly anisotropic layer. What we wanted to understand here was what impact could this anisotropy have on our final migrated image. So we modeled this using AxWAVE with an acoustic TTI model. And on the bottom right here, I'm showing you the model that we generated. So the velocity is in color, slower velocities in green, into much faster velocities in red. So we expect a nice strong reflector off this horizon. The surface is up here between the green and the blue, and the dip is annotated with these sticks, the direction and steepness of the dip. So I just wanted to show a few wave field snapshots through this model to show you how the wave field complexities can impact our imaging. So On the left, I'm showing a snapshot from a shot that would have gone off sort of around here somewhere, and you can see that the wave field is not expanding spherically. It's bulging out in areas where the wavefront spent more time traveling parallel to bedding, which would be a faster direction, and it's time delayed in areas where it spent more time traveling perpendicular to bedding. Now, if we take that a bit further, once we get to, if we take that a bit further, once we come back up to surface here, we can see more wave field complexity caused by the image going through. Here. Excuse me for 1 minute. There. Okay. Sorry about that. Okay, so we're seeing more wave field complexity as we travel through different fast and slow velocity regimes through different parts of the wavefront. So really what we were trying to understand here is how this will impact our seismic modeling, or our migration. And so what I did is I migrated these model data with 2 different dip models. So using the same velocity model but with a different dip model. On the left here I'm showing the results of migrating using the correct dip model, and we get a nice sharp image back. And on the right I'm migrating with a simple dip model. So this is ignoring those complexities in the dip model and just applying a broad dip model to follow the structure. And you can see that we get a much better result when we use the correct dip model. That's maybe fairly obvious. We also added some noise to our model data before we migrated, and it was very difficult then to see how far this reflector came over to this side. So I think this demonstrates the importance of using an appropriate dip model, and we were able to use these results to refine our model building process on this project. So that was a simple example about anisotropy. But more often what our challenges are is rapid near-surface velocity variation. And so in order to evaluate this, we used the BP94 statics benchmark model. It was created by the Amoco Tulsa Research Lab in 1994 to study statics and land data. It's a 2D model, 60 kilometers long, 6K deep, with 5 by 5 meter sampling. And even at this scale, you can see it contains a lot of near-surface features that are thought to be responsible for statics. We're focusing on the right third of the model I've outlined in black here and sort of zoomed in on the bottom. And I've plotted the surface in white. So you can see there's about a 1,000 meter elevation change over the course of the model and lots of detail on the near surface. We're going to zoom in on a few areas, and on the top left now I'm highlighting an area where we've got very slow weathering of 800 meters per second with a thickness varying between 20 and 50 meters. That's going to cause a lot of wave field distortion in our model results. And on the right, showing a really thick weathering package of about 300 meters that'll cause quite a large time delay in our data. There's also this interesting spot here where we have a much slower subweathering velocity coming up towards the surface, and you'll see that impact our first arrivals. We modeled these data using an acoustic isotropic model, shot spacing of 40 meters, receiver spacing of 10 meters, and using a 25 hertz Richter source wavelet. And I'm just showing you 3 example shots here that show you how complex these data do look. Now the numbers in the shots correspond to the numbers on the model, so you can see where those shots are. And you can see that because of the complex subsurface and all the detail on the near surface, we do get some fairly real looking data. And I'm going to zoom in on shot number 2 here and just talk through it a little bit more. So this is shot number 2 from the previous slide with the model below it at the same scale. So you can really see what's causing these wave field distortions here. They relate directly to where we have the complex near surface. And I say wave field distortions as opposed to static change because it's not really a simple time shift. It's much more complicated than that. So that's something we'll talk about a bit later as to what we can apply for a static and what we need to compensate for with a model. Over on the right, you see this huge time delay due to this thick weathering pocket, and then, as I mentioned before, on the right here, where we have a slower velocity coming up to the near surface, we see a massive delay in our first arrival times as expected. So the first thing we did is we took these model data and migrated them using a Kirchhoff pre-stack depth migration. I'm showing the result of that on the top here. And on the bottom, for comparison, I took the derivative of the velocity model and applied a filter to a similar bandwidth so we can see what reflectivity we might expect to see. Now, the results don't look very good. You can see in areas where there's maybe a simpler velocity model in the top left here, we get some of the reflectivity back, but we're not seeing a very good image throughout. So why is that? What's limiting our ability to image this? There's several things, but the first thing I wanted to look at was the resolution of the ray tracing for the travel times in Kirchhoff migration. And typically we have a much simpler model. This is a very detailed model, obviously, but when we build a real Earth model for our production projects, we don't have this much detail. And so we've optimized our ray tracing for simpler and smoother models. So this just highlights that here. I've just zoomed in on that same area and zoomed in even further, and you can see how much detail there is in the near surface. And we did apply slight smoothing when we migrated the data just to stabilize the migration, but still we're not going to be able to capture these sort of effects with our current ray tracing. So we resampled the ray tracing quite significantly, reran our travel times, and we get this result. So now on the top I'm showing our Kirchhoff PSDM with the real model, like I said, with slight smoothing on the model and with updated travel times. And you can see now that we're capturing a lot of the reflectivity, but in some areas, especially where I was pointing out before under these complex near surface areas to the left and also over here to the right, we're still not getting a very clear image. So what else can we do? Well, we can definitely further increase the resolution of the travel times, and we've done that, and it does improve the image. That becomes computationally expensive. It's not a real big deal on 2D data, but it's not really needed because on the real data project, in our production projects, we obviously won't have the real model. We'll have some sort of smoother model that represents the subsurface, and we'll try to build that with the following workflow. We'll run first arrival tomography to produce refraction statics in a near surface model. We'll supplement that with shorter wavelength statics from the reflection data. And we'll blend that near surface model with the deeper interpretive model that I talked about in the earlier slides. Then we apply some statics to our data and migrate. So what I wanted to try to do is replicate that scenario with this data where we have the real model. So I'm seeing what happens if we smooth the model and supplement with statics. I want to talk briefly about statics before I show you the results. And the big assumption with statics is that we're correcting for velocity variations that aren't built into our model, but we're assuming that there's a vertical ray path through the near surface. This is fairly close when we have our weathering velocity much slower than our sub-weathering velocity, and we're in areas of simple geology. And that's sort of the case I'm showing in the upper right here. And it breaks down in scenarios like I'm showing in the bottom right here, where we've got strong lateral velocity variation and complex geology. You can see there's a lot of non-vertical ray paths here. And so we just need to be careful about how we apply our statics. We can't go ahead and correct for all of this with a static correction without sacrificing some of the wave field propagation. Okay, so here is on the top a zoomed in version of our unsmoothed model. And I've put a base of weathering I'll use to calculate statics with that white line. And then on the bottom, I've smoothed the model. And this is maybe fairly optimistic on my part. You most likely wouldn't get this resolution from running first arrival tomography, but for this case, I wanted to keep a fairly good model to test this out. And I wanted to keep sort of features like this I'm pointing out here at around CDP 1400, where we've got some fine variation here. I wanted to keep the sort of smooth version of that, so we still see that complex ray pathing, but we smooth out the edges and get rid of the really fine detail that might be causing some problems in our migration algorithm. I then computed statics from the surface to the base of weathering and back up to the top final datum for both these models, and I'll show you what the statics look like. So here, the statics from the exact model are shown in blue, and the statics from the smooth model are shown in green. And you can see that in places, this is one way, these are just the receiver statics, and you can see in places there's an up to 50 millisecond static difference between the two, which is quite a lot, considering we didn't really smooth the model that much. And so what I did here is to use the smooth model for migration. I wanted to move the data to a static correction that would allow us to use that model. So I applied the difference of these statics. So applied the difference between the green and the blue curve to the data, and then migrated with that smooth model. So on the top now I'm showing the result you've seen before, which is the Kirchhoff PSDM using the real model with the updated travel times. And on the bottom I'm now showing the results of using the smooth model with statics. And overall you can see the image looks sharper. We're doing a better job of resolving some of those areas with the complex near surface. And I'm going to zoom in on a few areas that I've highlighted in these blue boxes. So starting with this blue box, or sorry, the white box on the left here. On the left, I'm showing now the results with the exact model and updated travel times compared to on the right with the smooth model and statics with our benchmark in the middle. And you can see at the zoomed in scale, there's quite a lot of reflectivity where we didn't see any before. And so we're definitely getting a sharper image. And if I look over to the box I highlighted on the right, same thing. We get a much sharper image, better false definition, better reflectivity. And so what we can say from this is that smoothing the model and applying the statics does improve the image. In terms of what the optimal smoothing is, that's something I haven't really determined yet. I've got some more testing. I've got some more testing to run on that. And can we compute the required statics? That's sort of the big question. We would typically compute those statics. If we had that smooth model that was representative of our more detailed model, we'd try to compute the leftover statics using a reflection statics method. And I'm not sure whether we'd get that real static field back. But it's a good indication that this workflow could help us in a production sense. All right, so those are the three examples I wanted to show. So how has TBI benefited from modeling using AxWAVE? Well, I showed you that using AxWAVE, we were able to better understand the impact of near-surface anisotropy. We looked at refining our ray tracing algorithm to work with higher resolution models. And I'm developing a workflow to incorporate more near-surface information into our model building process. Those are just three examples of how we've used AxWAVE. I've also run AxWAVE on several production projects recently just to try to understand some imaging artifacts I was seeing that I didn't quite understand from the migration process. For further work, I'd like to continue using this BP94 model. I will try to use the first arrival information to build refraction statics and see what sort of resolution model I can come up with. And I'll supplement that by calculating reflection statics. And then I do want to expand this into a 2.5D modeling study. So expand the model laterally and then shoot a 3D geometry over the model. I also want to use AxWAVE to test model-based move-out versus normal move-out. So ray tracing through your model as opposed to applying a simple normal move-out. I have a colleague, Dennis Ellison, who's working on his master's on that topic right now. And I have some ideas about how to use AxWAVE for helping us with our velocity model updates. And ideally, the real goal this year is to wrap all this up and develop a workflow for use on production projects. I'd like to thank Acceleware for organizing this webinar and also for their help getting us up to speed on AxWAVE. And I'd like to thank Mark Langlois and Rob Bestrom of TBI for their help on this project. And finally, thank you for attending the webinar. We'll have some time for questions, but Eric wants to say a few comments first, so I'll pass it back to Eric.
Yeah, thanks, Greg. Great examples. I think Greg is going to start looking at some of the questions that have filtered through here, and we'll address them here very shortly. So the importance of getting a better understanding of challenges in complex geology is that much more important, especially in areas where land is complicated to what we get access to. The complexity of getting equipment out there is very expensive, and your prospects, your exploration costs are very high. So why not take the extra effort and get a better understanding of the subsurface through some modeling exercises such that you're lowering your risk and you've got a much better understanding of where you're working. So how do you get access to technology like AxWAVE? We sell our technology through partners. We have partners that resell our technology. Paradigm, Open Geophysical, Tsunami, Geotomo resell our technology, and you can have access to that through their workflows, through their own software products, and you can buy it directly from us. And you can also access our technology through the cloud. We have a cloud provider called Nimbix. You see the web link there, nimbix.com. Log into there, and you can have access to AxWAVE to run your modeling. Finally, we'll be at the SCG in a little over a week's time, and we'll be presenting AxWAVE along with our other products, but we'll be presenting it live through the cloud. So come by and see us, and we'll be able to show you more information and get a feel for the touch of running the software. If you want to contact us, here our contact information is on our website as well. When you registered, you saw this information here, so you can contact us at Acceleware if you're interested in the technology, and if you're interested in the work that Thrust Belt Imaging is doing. Please feel free to contact Greg and his team out there. So I'll pass it on to Greg for the questions that have popped up, and then we'll conclude.
Okay. Thanks, Eric. And please, if you have any last-minute questions, please feel free to type them in. We got a few minutes here. The question I'll start with here is asking about model-based move-out. So could you give me more information about the model-based move-out? So I just talked about it in my conclusions a little bit, but the idea is that that if you have a velocity model that you're going to use for depth migration, rather than in your time domain before you migrate, rather than applying simple normal move-out, which could be a simple two-term move-out or even higher order, but still basically a 1D correction, you can ray trace through your velocity model and get a better approximation of flattened gathers to run things like reflection statics. So that's something that we've looked at in the past and are hoping to build into more of a production setting. And I do have I'll have a presentation on that a little bit later that I maybe can upload to this link for the webinar as well. Okay, so another question I've got here is, okay, so for the anisotropy model, what values epsilon and delta were used, and was this tested, and how did you decide on how the dips tapered with depth? So for that, let me go back to this slide that I was working on. Just give me one moment here. So basically the delta value was 3% and epsilon we used 20. And that was based on our understanding that this layer was highly anisotropic. Those are the values at surface, and actually the epsilon tapered down to 12% as we got closer to our red reflector here. In terms of the dips, we had surface dip measurements that showed us really steep dips at surface, and we assumed that those would gradually decrease and become more flush with this surface down here. We did test epsilon and delta somewhat. Obviously, if we reduced those values of epsilon, we got less of an effect on our data. But based on our understanding of the layer, we thought that those estimates were fairly reasonable for delta and epsilon. Okay, I think that's probably the time.
Yeah, I think we're
that we have for the webinar. So
running out of time. So there's a few more questions that have popped up, but we'll get to them fairly shortly here, and answer these questions in a follow-up email to all of you. As I mentioned before, we have recorded this webinar, and we'll have it uploaded up on our website, and I think Thrust Belt Imaging will have it up on their website as well. So you can feel free to review it at a later time and share it around your organization. Again, I'd like to thank everyone for attending, and Greg and the fine folks at Thrust Belt Imaging for presenting this webinar. Thank you, everyone. Thank you for attending.